rate of change. What is the rate of change? Firstly, I'll give you the technical explanation in order to know what is the rate of change. The rate of change is the speed at which a variable changes over a specific period of time. ROC is often used when speaking about moment, and it can generally be expressed as a ratio between a change in one variable relative to a corresponding change in another graphically. The rate of change is represented by the slope of a line. The ROC is often illustrated by the Greek letter delta. Okay, that was the technical explanation that was taken from Khan Academy. But now, in order to understand very well what is the rate of change, I have an example. And now that we are in the same spot, we can start to talk about it that can be related about our daily life. For example, this drop of water that falls in water make a circle in the water that is becoming bigger during the time pass, and with that we have two things that are related: the time and the radius that is bigger during the time pass, giving us a rate of change between the time and the length, and with that we can calculate, for example, in 3 minutes, what will it be the radius of the circle. Okay, that was an example, and now we're going to use the same example with a problem. For a drop of water that falls in water, we know that its radius increases at the rate of 1 centimeter per second. What is the rate of change of the area of the circumference when the radius is equal to 5 centimeters? Okay, that sounds strange or like something old, but it's really easy to do. First, in this problem, they are telling us that the rate of change of the radius is 1 centimeter per second. The rate of change of a magnitude is its derivative with respect to time. Okay, therefore, we have this. With that, we have a derivative that is equal of 1 centimeter per second. Then, what we have to do after this? They were asking us the rate of change of the area of the circumference when r is equal to 5 centimeters. That is the derivative of the area with respect to time. With that, we have two things: the derivative of the area divided by the derivative of the time when the radius is equal to 5 centimeters. But first, we have to use what we have. We have the radius, only the radius, and what we have with the radius and is related equal to the area, the formula of the area for sure. Then we have this. And this is just to help us to include this in this. Okay? And now we're going to, in the first part, we have derivative a with respect to t, whose derivative is a, as we see here, and dt, as we see. But now we have first to derive the both sides of the equation with respect to time, because it's in order to have an equal thing in this place and in this place. Now we have the time here, and with that we can start to advance in the problem. In order to solve this, we use the chain rule that is from outside to inside. The derivative of r is 2r, and we multiply it by the derivative, which is divided by dt here. With that, we derive all, and we just have to substitute the data that the statement gives us. Here, the statement gives us radius equal to 5 centimeters and the rate of change of 1 centimeter per second. And now we just have to put it on the formula that we used before. And with that, we have the most important part here. Okay, the problem when it is explained in this way maybe it sounds easy, but the thing is that we fail in one thing that is really important at the end: the units. The units are very important in that kind of problems, because if we finish and we just put 31.41 centimeters, it is totally wrong. We have to take in account that the centimeters here and the centimeters here, they have to multiply and have this 31.45 centimeters to 2 besides s, the seconds. That is the correct answer, and we have to take a look about the units in the whole problem in order to have a good answer. And that's it. Thank you, and continue.
Derivatives. Derivative is a function of a simple variable at chosen input value. This means that it's to find a specific value considering another factors, for example, a relation with time and space. There are some rules of derivation, and we have the constant rule that says that every derivative of a constant will be zero. We have the exponent rule, where the derivative of a function with an exponent is solved by multiplying the exponent by the function and subtracting 1 unit to the exponent of the variable. We have the derivative of a constant by a function, where we put away the constant and we derivate the function. We have the sum rule, where we have two functions f and g, and we derivate the function f and we sum it to the function g derivated. We have the product rule, where we have two functions f and g, and we multiply the function f by the derivated function g plus the derivated function f multiplied by g, the function g. We have the quotient rule, where we have the function f derivated by the function g minus the function f by the derivated function g over g to the square. We have the special derivatives with trigonometric functions with sine, cosine, tangent, cotangent, secant, and cosecant. We have the special derivatives of logarithmic and exponential functions that are so important. And we have an applicative problem. And it says, a study is conducted to obtain the decrease of employees that have been replaced by more efficient production machines over the years in an assembly factory. The function 2195 multiplied by Euler to the minus 0.3 t shows the number of employees removed in t years from 2015. Calculate the decrease of employees in 3 years. So, in the first step, we derivate the function to get the rate of change, and in the second step, we apply the rule of the constant by a function. In the third step, we use the special rule of the exponential numbers, and we obtain the derivative of this function. And in the fourth step, we simplify the function, having this result that will be the rate of change that we are going to use. So in the fifth step, we evaluate the number of years required by the problem, in this case 3. So we put this number here, and in the step 6 we have the result that is approximated to 268 employees less in 3 years.
The L'Hopital rule is a technique used to evaluate limits of indeterminate limits. The application of the rule often converts an indeterminate form to an expression that can be easily evaluated by substitution. The L'Hopital rule states that for functions f and g, which are differentiable on an open interval I, except possibly at a point c contained in I, if the limit fx that tends to c is equal to the limit of the function g that tends to c is equal to 0 or equal to plus or minus infinite, and the derivative of the function g is necessary that it isn't 0. For all x in I with x different than c, and the limit of the derivative of the function f divided by the derivative of the function g that tends to c exists, then the limit of the division of the two functions when then tends to c will be equal to the limit of the derivative of each function that tends to c. So why we need to use this rule? Well, as I mentioned it before, we use this rule when we have an undeterminate limit, like in this example. So if we evaluate the number 3 in the x's, we will end up having this as 0 divided by 0, which is undeterminate. So in this case, what we need to do is to apply the L'Hopital rule. So we're going to derivate the numerator and the denominator, and we will end up having this function. And now we're going to evaluate the limit of the function when it tends to 3, and the answer is 6, as you can see here. Another example could be this one. So if we evaluate the 0, we will end up having another 0 divided by 0 result, which is undeterminate. So in this case, what we are going to do is not to apply the L'Hopital rule one time. We're going to do it several times So as you can see in here, we derive the function, the function of the numerator and the denominator. We end up having this, but if we substitute the 0, we will end up having a 0 divided by 0 division. So we need to derive the function again. But if we do it, we will end up having the same issue. We will have a 0 divided by 0 result. So we are going to do it one more time, and in this case we are going to have a result that is not undeterminate. So we substitute the 0 in this function, and the result is 6. So now some questions. When do we use the L'Hopital rule? Solve this limit, and finally, if the derivative of the function of g is equal to 0, can we use the rule?
New methods. Well, the object of calculating the roots of an equation is to determine the x values for which is the limit. We'll give a first go to solution fx equals 0, a graph of g equal fx called width. Use the first approximations to get the second to get 13, and so on, using the formula here. For calculating. This is important, it's that if we can determine the roots of an equation, we can also determine highs and lows, matrix values, solvable system, or linear, and differential equation, etc. That is an application of differential calculus used to find the zeros, and in order to degree differentiable function, we decide the procedures to find the root zeros or of a linear quadratic function from the coefficient of the equation, or simple and exactly out of there are formats to find the roots of 3 and 4 degrees. Well, without an explanation, short is this is an application that we can all understand, and we can all understand needs to be an equation even if we don't understand the physics science behind an actual application.
Newton-Raphson's method is an iterative method whose function is to approximate the roots of an equation. Iterative methods work by starting with an approximate solution to the equation, either made up or by looking at the graph of the function. Then, to that first approximate solution, we apply a formula and we get another solution more like the true solution. Now, to that second solution, we apply the same formula again and we obtain a third solution that will be even more similar to the true solution, and so on. Each formula to obtain a new approximation is called an iteration. This iterative method uses this equation in such a way that each new approximation is equal to the previous approximation minus the result of dividing the value of the function that we want to solve in that previous solution by the derivative of the function at the same point. Then, the materials we need is to approximate first value and know the derivative of the function. Graphically, Newton's method works as follows. We calculate the tangent line to the function at point x1. We look at where that tangent cuts the x-axis, and that cutting point will be our new value x2, the same value that we will obtain if we only apply the formula. And we continue like this until the end closest decided value. Now, let's do an example. They ask you to find a good approximation of the root of the following function, and we take x1 equal to 1, for example, as a starting point. In the requirements, it says that we must have a starting point and know the derivative of the function. So, we use the power rule in each term to find the derivative of the function. Now, we can calculate the second value by applying the formula to the first value. So, we adapt our equation, we substitute, and we have our second value equal to 1.5. We apply the formula to the second value, and we have that the third value is 1.34782. We continue applying the formula to the third value and the fourth value. If we stay here, we see that between the last iterations there are two decimals in common. Then, we can conclude that in the fifth iteration we have a result for the root, with 2 decimal places of precision. Here is a little trivia for viewers. If you want, you can pause the video.